Welcome, my friends! In this video, we will be discussing the one-sample mean hypothesis test. If you've not watched my previous videos introducing hypothesis testing, I would highly recommend that you check out those videos first before watching this one. The procedure for testing the population mean in a nutshell is to first formulate a hypothesis about the population mean mu that you would like to research. This will typically be that you believe the true value of the mean to be either greater than, less than, or not equal to some stated value. Next, gather a sample from the population and see if the data is consistent with your hypothesis. For example, if you hypothesize that the population mean was less than 100, finding a sample mean that is less than 100 would be consistent with your hypothesis. Finally, if the data is highly consistent with your hypothesis, you will conclude that your hypothesis is most likely correct. Otherwise, you will dismiss the hypothesis. Exactly what is meant by highly consistent relates to the p-value, which we have discussed in depth in a separate video. There are many assumptions for the one-sample mean hypothesis test. The first one is that you must have a random sample, meaning that every individual in the population must have an equal chance to be chosen. Secondly, if the distribution of the data is normal, any sample size will work. Otherwise, your sample size should be at least 30. This is a central limit theorem requirement, and ensures that the distribution of the sample mean is approximately normal, which will allow us to use the t-distribution. Note that these are the exact same assumptions needed for the confidence interval on the population mean. In order to complete the hypothesis test, you need to calculate a test statistic from your sample, which is a t-score. The t-score can be found using the following formula. Take the sample mean x bar, subtract the stated population mean mu from your null hypothesis, and then divide by the estimate for the standard error of x bar, which is just the sample standard deviation s divided by the square root of n. Of course, whenever we use the t-distribution, we must have degrees of freedom, which can be found in this case by taking the sample size and subtracting 1. There is a different test statistic that uses the z-distribution that you may have come across, but that one requires you to know the population standard deviation sigma, which is unrealistic in most situations, so I don't use it. Alright, let's look at an example. Suppose the mean age in America is 38 years old. Sam believes that the mean age of Michiganders is different from 38. From a random sample of 25 Michiganders, Sam finds the mean age to be 34, with a sample standard deviation of 20. Is there sufficient evidence to suggest that the mean age of Michiganders is different from the American average of 38? Assume that the distribution of Michigan ages is approximately normal, and use a 0.05 level of significance. Let's record down some of the given information. The mean age in America is claimed to be 38 years old, and we are curious to see if this value is also the mean for Michiganders. This is a statement relating to the population mean mu, so we have mu is equal to 38. Our sample size is 25, so we have n is equal to 25. From the sample of Michiganders, the mean age was 34, which means that our sample mean, x bar, is equal to 34. The sample standard deviation was also calculated and found to be 20. At this point, we are ready to go through the 3 steps of the hypothesis testing procedure. Step 1 is to write out the null and alternative hypotheses. The null hypothesis always has a symbol that indicates equality, and in this case, that is that the population mean is equal to 38. This age applies to all Americans, and Sam thinks that the mean age for Michiganders differs from this value, but he doesn't suggest anywhere that the true age is either higher or lower than 38. That means we have a two-tailed test, with a not equal to sign in the alternative hypothesis. The phrase is different from also is a strong indication that this is a two-tailed test. If there was wording somewhere in the problem that suggested that Sam thinks the true age is higher than 38, then we would have a greater than sign in the alternative hypothesis. And if Sam thought that the true age was smaller than 38, then we would have a less than sign in the alternative hypothesis. Next, we can move on to step 2, which is the calculations, and includes finding the test statistic and the p-value. The test statistic can be found by this formula, which we looked at earlier. X bar minus mu divided by s over the square root of n. Plugging into the formula, we have 34 minus 38 divided by 20 over the square root of 25. I've included parentheses in the formula to hopefully stop you from making a calculator input mistake. If you type this into your calculator exactly how you see it here with the parentheses, you should get -1 as the test statistic. We can draw the t-distribution, which we know is centered at t equals 0. Our calculated test statistic is t is equal to -1, but since we have a two-tailed test with a not equal to sign in the alternative hypothesis, we need to account for a corresponding t-score on the opposite side of the distribution, at t is equal to +1. The p-value is the combined area in both tails of the distribution. To find the p-value, we will need to use the TI-84 calculator function called tcdf. To use that function, we need to know the degrees of freedom, which are n-1 or 25-1, which is equal to 24. On the calculator, press second, vars, which will get you to the distribution menu. Scroll down and press enter when you are hovering over the tcdf function. Our goal is to find the area in both tails of the distribution. The way we do this is by calculating the area in one tail and then multiplying by 2, since the distribution is symmetric. Typically, you calculate the area in the tail that corresponds to the side of the distribution that the test statistic was on. In this case, t is equal to -1. The area in the left tail goes forever in the negative direction to -infinity, so we will type in a really small number for the lower bound. I use -1000, which represents 1000 standard deviations below the mean, which is plenty small enough. The upper bound is our test statistic of -1. The degrees of freedom are 24. If you press enter when highlighting over paste, you will see this output. Match this output on a TI-83 calculator. tcdf -1000, -1, 24. If you press enter, you will get 0.16364. This is the area in the left tail. If you had a left-tailed test with a less than sign in your alternative hypothesis, this would be your p-value. Since we have a two-tailed test, indicated by the not equal to sign, we have to multiply this value by 2 to account for the corresponding area in the opposite side of the distribution. If we multiply by 2, we get the p-value, which is equal to 0.3273, which is the combined area in both tails. We know that the opposite tail also has an area of 0.16364 because the t-distribution is symmetric, so the area greater than t is equal to 1 should be the same as the area that t is less than -1. To properly show your work for this problem, you should write this: 2 times tcdf -1000, -1, 24 is equal to approximately 0.3273. This is the probability that we draw a sample mean of 34 or more extreme, assuming that the true mean is the value stated in the null hypothesis, 38. So there is about a 33% chance of getting a sample mean this far away or farther from the stated population mean of 38, if 38 truly is the mean. This tells us that our sample results are relatively consistent with the null hypothesis, as we would get results about this extreme about 33% of the time, even when the null hypothesis was true. So in other words, we do not have very good evidence against the null hypothesis. Next, we are ready for step 3, which is to make a decision to either reject or fail to reject the null hypothesis and to write a conclusion. We make our decision by comparing the p-value to the level of significance. The level of significance is 0.05, which was stated in the problem. The p-value is 0.3273, which is greater than the 0.05 level of significance. The p-value is high, so the null will fly, meaning we should fail to reject the null hypothesis. Remember that we reject the null hypothesis if the p-value is less than or equal to the level of significance, and we fail to reject the null hypothesis if the p-value is greater than the level of significance. Our conclusion is that at the 5% level of significance, there is not enough evidence to suggest that the mean age of Michiganders is different from the American average of 38 years. Remember to use is not when you fail to reject the null hypothesis, and is if you were to reject the null hypothesis. Alright, that finishes up our example. There are just a few things I should mention in closing. We had a two-tailed test indicated by the not equal to sign in the alternative hypothesis, as we weren't sure if the Michigan average was greater than or less than the American average. If we had a hunch that the mean age was either greater than, or perhaps less than, 38, then we would have either a right or left-tailed test, which would change the inequality sign in the alternative hypothesis to either a greater than or a less than sign. In that case, you would only have to find the p-value corresponding to a single tail in the distribution, meaning we would not have to multiply our p-value by 2. Also note that in some problems, you could be given data instead of statistics. So instead of being given x bar is equal to 34 and s is equal to 20, you might be given a dataset with numbers and asked to complete a hypothesis test with the numbers. In that case, you will have to calculate x bar and s using 1-bar stats on the TI-84 calculator. You would need to go to Stat, Edit, and then press Enter. Then you would enter the data into list 1. Press Stat again, arrow once to the right, and select 1-bar stats to get the statistics that you need to complete the test. Alright my friends, that wraps up our example relating to a hypothesis test on the population mean. Make sure to check out my other videos for more fun and exciting mathematical and statistical topics.